Standard electrode potential. Standard electrode potential is this value meant for these half equations that's taking place. As seen in your data booklet, all the equations are reduction reaction, where the oxidation state would have actually decreases, and in this case, it decreased from 0 to -1. And the number of the standard electrode potential quantifies how much the reaction will be able to shift forward. Hence, in this case, if the value is plus 2.87, which is considerably a very highly positive value, then fluorine would very easily reduce to form F-. And that is in line with our observation that fluorine is a very good oxidizing agent. Conversely, if you now take a look at this half equation, where the standard electrode potential value is minus 2.92, if the value is extremely negative, it means the backward reaction is strongly favored. In this case, what that means is that potassium easily oxidizes to form K+. And that is also in line with what we have observed, since potassium is a very reactive metal and easily oxidized, therefore making it a very strong reducing agent. Bear in mind all the equations that we are going to study in the data booklet. The left-hand species are oxidizing agent and the right-hand species are reducing agent. So for example, V2 plus will gain 2 electrons. So V2 plus would be a left-hand species and therefore an oxidizing agent, while vanadium is actually the right-hand species. So therefore it will be a reducing agent. And certainly in this case, if the value is negative 1.2, then it is more likely that the backward reaction is favored. Hence, vanadium is more likely to oxidize to form V2+. With that, let's take a look at standard hydrogen electrode. Standard hydrogen electrode is to be used as a reference electrode, where the platinum catalyzes the setup of the equilibrium, where the half equations is as such, and the standard electrode potential value is set as 0. It is somewhat set as the datum. So this is actually the sketch itself, and mindful that all the gases, the pressure will be 1 bar and the temperature is 298 Kelvin. And the concentration of your ions that is used in all the solution, in the aqueous solution, is 1 mole per dm³. With the understanding of standard hydrogen electrode as a reference electrode, you can now look at the definition of standard electrode potential. The standard electrode potential that you've seen in the data booklet is defined as the potential difference between a standard hydrogen electrode, which serves as half of the electrode, with the other half of the electrode possibly being actually a metal immersed in a solution containing metal ions. For example, we can look at these half equations, where in this case, the electrode will be copper and the ions will be Cu2+. And the concentration of the Cu2+ will be 1 mole per dm³ at the standard conditions of 298 Kelvin, 1 bar. Alternatively, the standard electrode potential of this equation is 0.09 volt, and that is actually defined, and that standard electrode potential value is obtained using standard hydrogen electrode as a reference electrode, and the other half electrode will now comprise of this ion at 1 mole per dm³, and this ion also at 1 mole per dm³, with platinum as the electrode immersed in the solution, and the standard conditions will still be at 298 Kelvin and 1 bar. We'll now take a look at how standard electrode potential values could be used, as well as what are the factors that affect them. Let's take a look at these two half equations, equation 1 and equation 2. It is clear that the E value in equation 1 is highly positive, which means in this case, X plus readily accepts the electron to form X rather than Y plus accepting the electron. Therefore, X plus is deemed to be the stronger oxidizing agent since it is a left-hand species. Conversely, if we were to compare the metal X and Y and to deem which is more reactive, the one that is less positive is more likely to oxidize as the backward reaction is favored, which means Y, which is a more reactive metal, is also a stronger reducing agent since X and Y are both right-hand species. Let's take a look at another set of half equations. In this case, you will find that in equation 1, it is more positive than equation 2. The difference is that X2 and Y2 are both non-metals in this case. And by looking at the standard electrode potential value, we can conclude that X2 is a stronger oxidizing agent, while in this case, Y minus is a stronger reducing agent. Now let us study these half equations and see what happens when we decide to increase the concentration of the OH minus. Using Le Chatelier principle, increasing the concentration of OH minus will shift the position of equilibrium backward. Since the backward reaction is now favored, it means the standard electrode potential value, which originally stand at 0.40 volt, will now have to decrease and go lower than that. Let's take a look at another equations. In this case, we're increasing the concentration of zinc 2+. If we increase the concentration of zinc 2+, the position of equilibrium will shift forward. Since it shifts forward, the standard electrode potential value will now be more positive or less negative. So in this case, the value will be less negative. However, if we were to increase the mass of zinc or increase the surface area of zinc, you will find that based on the Chatelier principle, the position of equilibrium doesn't shift, as changing the concentration of a solid does not affect the position of equilibrium. So based on that, the standard electrode potential value remains as negative 0.76. Finally, let's take a look what happened if we were to increase the partial pressure of oxygen. If we increase the partial pressure of oxygen, the position of equilibrium would, based on the Chatelier principle, it will favor fewer gaseous molecule, so the position of equilibrium will shift forward. So in this case, the standard electrode potential value will be more positive than 0.40 volt. With the understanding of all this, we can now look at para 4b of your data booklet, where the potential value is lined up in such a manner that from bottom to the top, the value of the standard electrode potential value is ascending. So with the highest value right at the top and the lowest value right at the bottom. Hence, in this case, we can conclude that fluorine is plus 2.87, chlorine plus 1.36, bromine 1.07, and your iodine 0.54. With that, we know that fluorine is the strongest oxidizing agent, while your iodine is the weakest oxidizing agent. Conversely, we can conclude to say that I- is the strongest reducing agent and F- is the weakest reducing agent. Therefore, it means that going up the table, the reactivity of non-metal increases. Let's take a look at metal. In the case of metal, all the metals are right-hand species. They are all reducing agents. And in this case, the more negative the metal, stronger its reducing power. Therefore, because of that, based on the table given in para 4b in the data booklet, potassium would be the most reactive and silver would be the least reactive. So going up the table, reactivity of metal decreases.